Hi, everybody. So I'm going to talk about some work we did at Dfinity on building an ECDSA signing service. And the big picture here is that blockchains, to succeed, need to talk to other blockchains and to the world in general. So we wanted to build a signing service as a way that smart contracts can sign messages. And along the way, we ended up being in a stage where we really had to do some hardcore cryptographic research. So I'm hoping to present the whole stack from what is it that the users want to all the way down to the cryptographic research we had to do. Brief background about the Dfinity Foundation. So we have close to 300 people working at Dfinity. It's a Swiss non-profit organization. And we really invested in, got some very strong researchers and engineers that have published lots of research papers. And a couple of years ago, we launched the Internet Computer, which is the blockchain-based platform. And we're hoping to take all traditional IT stack and put it on blockchain. So that's our goal. And these are the dApps that are building on porting Web 2 space to the Web 3 space. And we've been running smoothly for a couple of years now. So let me zoom out and not focus particularly on the Internet Computer, but I think on a question that will be on all of your minds, right? Will blockchain eat software, right? And Dfinity's thesis is that indeed smart contracts have so many advantages that eventually they ought to replace the legacy IT stack, okay? We think this is a good thing with the security and user protection smart contracts can bring. This picture is not to scale. Right now, the smart contract is a very small fish compared to the rest, but we are hoping that it will increase in the future. And we don't think we've proven that, but what we think we have proven is that it's a plausible thesis, and we will then see over the next decade how it plays out. So to take a step back, what do I even mean when I say blockchain will eat the world, right? So blockchains can be like pieces of data and they are hashed together. That's like the core of it, where the word comes from. But then you need a blockchain protocol that describes how do these nodes work together and reach consensus about the blocks and the ordering of the blocks, right? And maybe some papers and research about that, okay? And then what we interact with is a blockchain platform where you have an implementation, you have some physical machines that are connected to the internet, they have some execution paradigm by which the dApps running on them work. And beyond that, you have a project, right, where you have some SDK that developers can use to build on the platform, and you have some way that the users can interact with the platform, and you have a community that agrees on how the blockchain should operate and so forth, okay? And it's really the whole stack that has to work well in order for blockchain to eat software. So two key requirements is performance, that you can actually have a performant enough system so you get a good user experience and people can use their phones or laptops or whatever to connect to the blockchain. And another one is integration, right? Basically, the smart contracts running on the blockchain have to be able to talk to the world. So to address the first question, can blockchains have competitive performance, right? And it's a challenge, because on a blockchain, you have basically the state of a smart contract, which is replicated across many machines. And whenever you execute something, all of them have to agree that this is the same thing that they're executing, and this is the next state they're reaching, and they're all in agreement, right? So there is clearly some overhead of running things on a blockchain. But we've actually shown in our research that blockchains can compete with traditional cloud computing, okay? So replicated state machines, so this is a message from the research, replicated state machines can compete with traditional serverless function as a service computing. And this is research we published at the prestigious Usenix ATC conference. Okay. What does it mean in practice? Okay, so the Internet Computer as a blockchain and the performance you can achieve, right? So we have read latency of hundreds of milliseconds, and that's the same as traditional IT because that's just the round trip time, right? To send some query on the internet. Write time, a bit longer because you do have to reach consensus that now this is what we want to update state to. But a second or two, that's still very acceptable for many applications, right? If you are running, a social media kind of application and it takes a second for a user to post something on their feed, that's fine. Okay, we have high throughput, and this is a system that's running in practice. We are processing thousands of transactions per second. And the smart contracts we have also really powerful. So we're talking about smart contracts that can store 100 gigabytes of storage at a very low cost. Okay? And as one of the comparison points with function as a service computing, typically they cap the limit at 32 gigabytes, right? So there we're actually doing better with smart contracts. And if you think about what is the limit of performance for blockchains, I think the unit of measure is energy consumption, and we are working at around 29 joules per transaction, so less than a light bulb second per transaction. Okay, so I hope I've convinced you that blockchains have the potential to have the performance that is needed to take over traditional software. The other aspect is the interaction with the world, right? So for blockchain to succeed, you have to interact well with the world. You have to interact with the users and give them a good end-user experience, right? Can a user take a browser, point it to the blockchain, and interact with the dApps on it? That's the kind of thing we're aiming for. We want a good developer experience, right? So we don't want developers to battle with having smart contracts on one blockchain and then doing some AWS computation on the other place, and you have to get those two to work together. We would like the developer experience to be that you just put everything in the smart contract, take the web front end that you want to serve to users, put it in the smart contract, and the blockchain platform takes care of it for you. Programming in any language you like, Rust, Python, TypeScript, Motoko, and so forth. And several blockchains have actually taken that approach, right? They offer smart contracts in WebAssembly, and you can just compile to WebAssembly. There's a question of how do you manage, how do you upgrade and evolve the blockchain platform, right? How can users come together and decide on this is like the next version of the platform so you can actually evolve and upgrade the software. And this is something we've done on the internet computer. We do actually have everything hosted on-chain, so users can go to the internet computer, vote on what is the next version of the software. If they vote yes to the upgrade, it automatically executes the upgrade, and you have the next version of the platform up and running. So we do on a weekly basis the equivalent of a hard fork. Okay, and I've given here on the slide as well a couple of links if you want to experience the experience that users have or see a sneak peek at the developer experience. Feel free to check those out. They should be directly accessible in your browser. There's no cloud computing service, AWS or something. It's hosted directly on the internet computer. Okay, and the thing I want to focus on right now, and where this research on ECDSA signatures that we did comes from, is in the interaction of dApps with the world, right? So the dApps running on the blockchain platform have to be able to interact with the world, get data from the world, send data to the world, okay? And we can offer a service where smart contracts can do HTTP requests. We are working on services so they can integrate with other blockchains. And in particular, I'm going to talk today about how dApps can interact with the Bitcoin network. Okay, so let's look at this from a smart contract perspective, right? That wants to interact with the Bitcoin network. And one thing it has to be able to do is to read the Bitcoin network and get, for instance, say, here's a Bitcoin address. What are the UTXO set for that address? And they also have to be able to submit things to the Bitcoin network, right? Let me say, here's a transaction I want to do. Please submit that to the Bitcoin network. And we worked on a communication integration that does exactly that. So basically, the nodes running the Internet Computer Platform reach out in multiple connections to validators on the Bitcoin network, right? In a way such that it's resilient, even if some of our nodes or some of the Bitcoin validators are malicious, it's still a robust connection. Okay? And remember I said that we have like a lot of storage capacity in smart contracts, right? So the Bitcoin blockchain is something like 9 gigabytes. We just import that into a smart contract, and it's ready in the Bitcoin service to be queried directly. Okay, so the catch here is that this is great. Now the smart contract can communicate with the Bitcoin network, but it can only, of course, the Bitcoin network is only going to accept a signed transaction, right? And as we know, a smart contract cannot hold a private key, right? Because it's replicated, and if any of those nodes that hold the data, replicated data, are malicious, they know the signing key as well. So what we wanted to do is then to provide an ECDSA signing service to the smart contracts. So the smart contracts can say, give me a public key, and the signing service says, sure, here's your public key. And it can say, sign this message, okay? And it says, here's a signature on the message. And now the smart contract is good to go and can interact with the Bitcoin network. Of course, we just moved the problem. Now the ECDSA signing service somehow has to manage the secret key, right? And this is where the cryptography comes in, okay? So you can use something called secret sharing techniques such that the nodes running the ECDSA signing service collectively have the secret signing key, but no single node or small minority of the nodes know anything about the secret signing key. And when it comes to creating a signature, we can run something called a secure multi-party computation protocol to sign the message. And again, it has the security properties that there's no single node or minority of the nodes that can forge a signature. And this is something that's been known since the 80s, right? So this is great. It's classical cryptography. And the tricky thing is to get the performance and the requirements right, okay? So we formulate different requirements we wanted for this. And one is that it should tolerate malicious corruption of the nodes, where they can do anything bogus kind of thing if they're malicious. It should also assume asynchronous communication, okay? So, and this is actually unlike a lot of the MPC literature, where you assume synchronous communication, nodes compute something, send something, next round, everyone reads the incoming messages, compute something, and send something, and so forth. And that's a very simple model. But reality is the internet is not synchronous. Sometimes a node is under denial of service attack, cannot communicate with the rest. And we also wanted to guarantee output delivery. Again, there's been a lot of research activity in ECDSA signing service functionality, but often they do not guarantee that you actually get a signature in the end. So it's sort of like a best effort. The problem now is that this is slow, okay? So we needed to do something that is efficient. So we looked around, what are the ideas? And here's one idea. In the ECDSA signature scheme, you first hash the message, then you do something. So imagine now we have a smart contract on one shard, the signing service on another shard, right? and it wants to send a message. It would be very expensive to transmit the whole message. Maybe it's a 1 gigabyte message. Okay? But instead, why don't we just send the hash of the message? And then we do this, what we call the raw signature on the hash. Of course, this raises a research question: is that secure? Okay? For the other two performance tricks, I need to just give a very quick introduction to the ECDSA signature scheme. The public key is a group element, capital D. The secret key is the discrete logarithm of that. And a signature usually two field elements, S and T. I'll, for simplicity, also include a group element R that can be computed from S and T, so there's no loss of generality. Okay, so the trick now is, instead of doing secure multi-party computation of everything at once, first, have a phase where you don't even need to know the message and compute this capital R. And that allows a much faster second phase. When you know the message, you can lightly fast compute the signature. The problem, again, from a security perspective is, right, is this secure? Is it okay to first pre-compute this group element R and publish that? And it was a good thing we did the security analysis, because it turns out that if you combine this with raw signatures, it's completely insecure. Final optimization tricks is key derivation. Okay, so imagine we have this ECDSA signing service. It manages 1 million different keys for 1 million different smart contracts. That's going to be expensive, right? It has to generate the keys, it has to replace them whenever there's a node that crashes, and so forth. And here the idea is that you can have a single master key instead. So you have one single public group element, and you just derive the public keys for the smart contracts by computing this public twig E. And there's already a standard for that, developed for different purpose, but we repurposed that standard, the BIP32 standard, that tells you how you can take a smart contract ID and derive this public twig. And now there's only one key to manage, right? So that's great. Again, security questions, is that secure? Okay, and it turns out, well, not so much in combination with pre-signatures. Okay, so we wanted to have all the optimizations, right? But there were some security problems. What do? We came up with a couple of mitigations. And one of those mitigations is, let's keep on doing pre-computation, but before we use the pre-signature, let's randomize it a bit again. And on the Internet Computer platform, it's easy to get pseudo entropy, so you can randomize it again. And now you actually, turns out, you get the best of both worlds. You defeat the attacks, but you still get the advantage of pre-computation. So we analyzed all these different combinations, pre-signatures, randomized pre-signatures, additive key derivation, the other mitigation, homogeneous key derivation, whether it could be raw or plain signatures, and so forth. Okay? And this is research we published at the prestigious Eurocrypt conference 1 year ago. And these are the outcomes, right? And what is left now is to choose one of those categories. We went with additive key derivation with re-randomized pre-signatures to get all of the optimizations at once. Okay? And that gives us the Bitcoin integration. Okay? It's still slow even with these optimizations. We are running at half a signature per second. But then again, Bitcoin is also running at 7 transactions per second, so that's fine. We did have the user developer reaction. Oh, you can do ECDSA signatures. Let's do that for everything. Let's do that for Ethereum. Let's do that for web authentication. So you can imagine one ongoing research question is, how do we improve the performance? We've also looked at another signature, Schnorr signatures, and there we can get much higher speed. And that's it. That's what allows smart contracts on the internet computer to directly hold Bitcoin and transact with Bitcoin and interact with the Bitcoin network. Thank you for your attention.
Thank you.